Hello everyone, let's try to solve the previous year questions from the alkyl halides chapter. Start solving these previous year questions. Let me explain you the important topic, which is nucleophilic substitution reactions, which are SN1 and SN2. Which are SN1 and SN2. So these are two important concepts, or you can say important mechanism that you need to know and you will use throughout your organic chemistry. And whatever it might be the reaction, they might include which one undergoes SN1, which one undergoes SN2. That you need to know the difference between these two, and you have to know when we can do this, or when we can follow these SN1 and SN2. All right. So what is SN1 means? It is a unimolecular nucleophilic substitution reaction, and this SN2 means bimolecular nucleophilic substitution reaction. So here it is 1. Why? Because the order of the rate of reaction is 1. It depends only on the substrate. Substrate means reactant only. This is the substrate. Here substrate is alkyl halide. Alright. Or you can say rate is proportional to stability of carbocation directly. And it is a two-step reaction that you can see here in this mechanism that I have explained you in detail. It is a simple mechanism. First, what will happen? First, leaving group will leave. Here it can be any halogen. This chlorine will leave and it will form this carbocation, right? And then nucleophilic attack can take place from front, or it can take place from back. All right. So if nucleophilic attack takes place from the front, we will get the retention product. Why? Because this chlorine and nucleophile are at the same side of this compound. So here the configuration got retained, right? That's why it is a retention product. And here if it attacks from this back side, then we'll get inversion product. Means the configuration got inverted. So chlorine is this side, means right side, but here the nucleophile is on the left side. That's why it is a inversion product. Okay. And this is to overall the mixture of this inversion and retention is called racemic mixture. Generally racemic mixture is optically inactive. Okay. Yeah, it is a two-step reaction that you have seen. First, leaving group will leave. This is the first step. It will form a carbocation, and in the next step nucleophilic attack takes place. Nucleophilic attack. Okay. So generally whenever you are seeing the rate of reaction for SN1, you can check the stability of this carbocation simply. So you can say rate is proportional to stability of carbocation. Okay. And intermediate is carbocation, and rearrangement can take place here, because see, as we know that what is the order of the stability of carbocation? Generally tertiary carbocation is more stable than secondary than primary. Why? Because tertiary, this is the tertiary carbocation. What is tertiary? Means this carbocation attached to three more carbons. All right. So this is tertiary. And here here there is an hypoconjugation. 9 alpha hydrogens are there. Sorry, here alpha hydrogens. How many alpha hydrogens are there? 9 alpha hydrogens. So through hypoconjugation also it is getting stabilized, and through inductive effect, plus I effect. Through plus I effect also this carbocation is getting stable. So that's why generally tertiary is greater than secondary and then primary. We just need to apply few GOC, general organic chemistry topics, like electron displacement effects. We have discussed this hyperconjugation and plus I, right? So that thing you need to have an idea. So before starting this chapter, if you complete that general organic chemistry, then that will be good start to see. Organic chemistry is like a series. You can't skip one chapter and jump into another chapter, right? While seeing series also, if you just leave one episode and if you see another episode, you won't understand anything, right? So that's how organic chemistry works. First you need to start with general organic chemistry, then you move to hydrocarbons, alkyl halides, all these things, so that you can relate those concepts over here also. And here I have written where it is. Yeah, racemic mixture, retention and inversion product will form, and it prefers weak nucleophile because it is forming a stable carbocation, right? I mean carbocation intermediate is forming. It doesn't matter is this nucleophile is weak or strong. It will attack over here on the carbocation because it is positive and it is negative. It will easily attack on this. It doesn't require any, I mean, strong nucleophiles as we'll discuss in SN2, and it requires polar protic solvents. Okay, and the order of reactivity is this: tertiary is greater than secondary, then primary halides. Because if it is tertiary halide, this is tertiary halide, and it forms tertiary carbocation. That is the reason why the order of the rate of reaction is this. So I hope you have understood this SN1 clearly. Now let's try to understand this SN2. Okay, so here SN2 is a bimolecular nucleophilic substitution reaction. So here it is a order of 2. Why? Because the order of this thing is 2. Here rate depends on substrate. I mean, it is a reactant, and at the same time it also depends on the nucleophilic concentration. Okay, and it is a single step reaction. Don't get confused. SN2 means it is a two-step reaction. No, no, we are talking about order in this case. That 2 refers to the order of the reaction. Okay, so it is a single step reaction and there won't be any intermediates, and no rearrangement takes place. That you can see through this example, or this is a simple mechanism that I have written here. This SN2 mechanism happen in a single step. Nucleophilic attack takes place, at the same time leaving group also leaves. Okay, this is how it occurs, and it forms a transition state where it is a pentavalent compound. And here we'll keep like this is a bond. There is a bond forming between carbon and nucleophile, and this bond between carbon and halide is getting cleaved. That's why it is shown by these dotted lines, and then leaving group leaves. Then we'll get this final product, which is complete inversion product. You can see the configuration got inverted. Initially the halogen is on, well, here, right on the right side, and the nucleophile got attacked from the back side. That's why it is a inversion product. So that's why we'll get complete inversion, which is also known as Walden inversion or umbrella inversion. Why umbrella inversion means, let's say for example the wind is so high and you are using that umbrella. Suddenly when wind hits the umbrella, like it turns outwards, right? So that's how we can also call it as umbrella inversion. And it is faster in less hindered environment. This is the important point. It prefers in less hindered environment, because see, let's say for example it needs to attack from the backside. If it is less hindered or less crowded, it can easily go and attack, right? If it is crowded with a big group, it's just have took it as like hydrogen. Let's say for example alkyl groups are there, big like large alkyl groups are there. There won't be any space for nucleophile to get attached to the carbon, right? So that's why it prefers less hindered environment, and strong nucleophile is required. Here there is no formation of any carbocation as SN1, so it requires strong nucleophile and require polar aprotic solvents. Why polar aprotic solvents means, if we take polar protic solvent, it decreases the nucleophilic character. That's why we will prefer polar aprotic solvents like DMS, DMS4, like that. Okay, dimethyl sulfide, these things. Okay, so that's how the difference between SN1 and SN2. I hope you have understood these mechanisms also. It's very simple. So in SN1, first leaving group will leave, then it will form a carbocation, then nucleophilic attack can take place from back and from front side. So we'll get racemic mixture. And in case of SN2, nucleophilic attack and leaving group does at the same time. So we'll get a complete inversion product. You just take a screenshot of this thing, or you can just write it in your notes itself. Okay, the difference you need to know. So I hope you have understood this topic. So just see once, we'll solve questions based on these topics now. Whatever we are going to solve, those are previous year questions only, so that you will get an idea how they'll ask exactly. So first question is this. So let's try to solve. Based on this concept, these questions, if you solve, your concept will get cleared even more better. Tertiary alkyl halides are practically inert to the substitution by SN2 mechanism. Why? I have already told you, right? For SN2, it prefers less hindered environment because the nucleophilic attack, it will be easy. That's why steric crowd and steric hindrance is the answer. Why tertiary alkyl halides are practically inert? Because of steric hindrance. Tertiary alkyl halides means there will be three different alkyl groups over here. These are might be bulky, right? So nucleophile can't able to attack from the backside because of the steric hindrance. So that's why option A is the correct answer. So I hope you have understood this. And then let's see this question. The structure of the major product, formed in the following reaction. So they have given this thing. Here one thing that you need to know. CH2Cl, this is I. This is the aryl halide, right? And here they have given NaCl and DMF. I hope you have understood. If they gave DMF, this is a polar aprotic solvent. So if you see this polar aprotic solvent, it prefers SN2. Alright. And also one more thing that I wanted to tell you here. Aryl and vinyl halides. Aryl and vinyl halides are won't undergo SN1 and SN2 under normal conditions. Okay, because what is aryl halide? This is the aryl halide only, like when it is directly attached to the benzene ring, or this is the vinyl halide and this is the aryl halides. Generally this is important point. Aryl and vinyl halides won't undergo SN1 and SN2, because if it undergoes like SN2, in case of SN2, see there will be resonance will be there in this ring, right? So in between, so here what happened means we can draw like this instead of this thing. So here this iodine, this halogen is connected with sp2 hybridized carbon, right? So here due to resonance it forms a partial double bond character. It gets a partial double bond character, and the bond becomes even stronger and shorter. So it's hard to break this bond. That's why it won't undergo the SN2. And SN1 means if you remove this one and if you form this carbocation, which is very unstable because it is not getting stabilized by this resonance. Also it is out of the plane, right? So it is not stabilizing by this resonance. It's highly unstable. Here is, this is also same case. This is highly unstable here. It is not even getting stabilized by the resonance, so it won't undergo SN1 and SN2 also. This is this halide is attached to sp2 carbon, right? So it won't. So that's why this is one of the important point. Generally, aryl and vinyl halides won't undergo SN1 and SN2. So now let's come to this question. So here, this, as we know that this aryl halide won't undergo this SN2. So generally, what happens? This Cn negative acts like a nucleophile and it will attack over this carbon, and this will leave, and we'll get this one CH2Cn. Here it is the iodine. Simple, right? Yeah. I hope you have understood and try to have an idea about this point. Yeah. And let's try to solve the next question. Sorry. Yeah. Let's try to solve the next question. Fluorobenzene can be synthesized in the laboratory. Fluorobenzene means this. Generally, we can't prepare this fluorobenzene directly as we prepare chlorobenzene and bromobenzene. So generally, we'll prepare this via diazotization. This is a famous reaction. If you have completed the amines chapter or overall organic chemistry, you will easily mark this one. First, we'll take aniline. Okay, and then we'll do diazotization by taking this reagent HCl in the presence of low temperature. It forms benzene diazonium chloride. This is benzene diazonium chloride, and in the presence of this HbF4, this will replace with the fluorine. So simply here we'll get fluorobenzene from this method. So here the option D is the correct option. Okay, let me write it. So option D is correct. From aniline biodigestion followed by heating the diazonium salt with HbS4. So I have also added the explanation why can't why can't these options like A, B, C can't happen. So generally this can't be prepared by using halogenation or substitution methods used for the we can prepare through halogenation substitution methods for chlorobenzene and bromobenzene, but we can't prepare this one because fluorine is too reactive, and direct fluorination of benzene, it causes more explosive reactions. So that's why option A is wrong, that they have given by direct fluorination we can't prepare. Okay, and also second option by reacting bromobenzene with NaF. So NaF can't displace bromine. So here NaF can't displace bromine in bromobenzene because aryl halides. I have told you, right? Aryl halides do not undergo SN1 and SN2. That's the reason why this can't replace this bromine in this bromobenzene. Okay. And last one, phenol with HF. It does not yield the fluorobenzene because OH group cannot be easily replaced by fluorine, F negative. So this is also wrong. So option C is D is the correct. Okay, I hope you have understood this. For your reference only, I have added this thing. Okay, yeah, and here they have given trans. So let's try to solve this question. Trans 2 phenyl 1 bromocyclopentane on reaction with alcoholic KOH. So here alcoholic KOH act like a strong base. It tries to abstract a hydrogen, and it generally it does an E2 elimination occurs over here. So let's try to draw this thing. Cyclopentane means 5 carbons are there, and 2 phenyl. If you take numbering from here 1 2 3 4 5, this is 2 phenyl and 1 bromo. On first carbon it is bromo, right? So now what happens means if we take in this with alcoholic KOH, so simply it undergoes elimination reaction. They have mentioned trans to phenyl. Generally this undergoes E2 elimination. For E2 elimination, the thing is that anti-periplanar configuration should be there. This, as they have given trans, this hydrogen. So it tries to obstruct this hydrogen over here. This OH negative will try to obstruct this hydrogen, and this bond shift towards here, and this bromine will leave. And here we'll get this compound. It will form an alkene, okay, over here, which is stabilized through resonance also. So what is the answer? 1 phenyl, we'll give numbering from here obviously. 4 5 1 phenyl cyclopentane. So option A is correct. Okay, and yeah, here it undergoes E2. And one more thing I just want to tell you, if they gave aqueous KOH, it undergoes substitution reaction. If it is alcoholic KOH, it undergoes elimination reaction. Okay, I hope you have understood. Let's have an example. Let's take this. In the presence of aqueous KOH, it just replaces this OH, chlorine with OH bus. If it is like alcoholic KOH, then it forms an alkene. Okay, it obstructs this hydrogen from here, and this bond shift towards this is not there. Just wait. So it will obstruct this hydrogen, and this bond shift towards here, and this will leave. So we'll get this alkene. So I hope you have got this difference, alcoholic KOH and aqueous KOH. Okay. This is generally called dehydrohalogenation. What we are doing, we are removing this hydrogen part and the bromine. That's why it is dehydrohalogenation. This bond shift towards here. When this base obstruct this hydrogen, this will this bond shift towards this one and this will leave. So that's how the it forms an alkene, and plus we'll get HBr. Here Br and Hu is getting removed, so that's why dehydrohalogenation reaction. Okay, and this is a simple one that I have so this is the simple question because I have already explained what is SN1 and SN2. You will understand, right? It prefers, again I have told you this is a very important point, prefers less steric, less hindered. So that's why generally primary uh, methyl halide is greater than primary, then secondary, then tertiary halides. This is the order of reactivity. Here they haven't given this methyl halide, so you can see this primary and secondary and tertiary. This is the correct option. How am I checking? Is it primary or secondary? You can just draw like this. See, H, H. This is X, right? And the second one, what they have given? Two R groups they have given, and one H is there. So here the carbon is attached to only one alkyl group, or it is attached to only one carbon, right? So that's why it is primary. And here it is attached to two carbons. That's why it is secondary. And remaining it is attached to three. That's why it is tertiary. So that's why that's how the order of reactivity is this. So the correct option is C. Okay. And yeah, this is also organochloro compound which shows complete stereochemical inversion during SN2. Complete stereochemical inversion which shown by SN2 reaction. C. I have told you it prefers less hindered. If it is a methyl halide, then if there is a nucleophilic substitution takes place, it can easily attack over here and this will leave. We will get CH3 nucleophile. In this case, it will be complete inversion. Okay. Correct. Okay. And here this is also correct. So this is also simple question. Here they are asking correct order of SN1. So SN1 means just try to remember that you need to check the stability of carbocation. Okay, you need to check the stability of carbocation. Here just try to remove the halogen and try to write the product. First this one they have given bromine. Here Me means methyl group only, that's why I'm just keeping it like this. First what happens in SN1, it is a two-step reaction. First bromine will leave and it forms a carbocation, right? And the next compound they have given this bromine. This Me means methyl group only, so we can draw it like this simply. This will leave and it will form a carbocation. Here it is a double bond. And one more is this bromine. So this is a simple question, okay? You just remove this bromine. Yeah. Now you need to check the stability of these carbocations. Now it's simple, right? So here this carbocation is getting stabilized through resonance and at the same time plus I effect also, right? And see, whenever there are multiple displacement effects are there, then you need to give the priority for resonance first, and then hypoconjugation, and then inductive. Okay, this is the order for in order to give the priority. A few cases are there, exceptional cases that where we'll give priority to hyperconjugation or something like this. We'll see those in my upcoming sessions also. Yeah, mostly will be the order that we'll prefer. So here resonance is, this carbocation is resonance stabilized. So this carbocation is resonance stabilized. And here this carbocation, what is the degree of carbocation over here? This one. This carbon is secondary because it is attached to two carbons, right? Secondary carbocation, and this is only attached to only one carbon, so primary carbocation. So this is primary carbocation. Generally, I have told you secondary carbocation will be more stable than primary because it is having 3 plus 2. 5 alpha hydrogens plus inductive effect. It is having only 2 alpha hydrogens plus only less inductive effect. So that's why here, let's say this is A, B, C, then obviously B is greater than C, then A, BCA. BCA is the first option. So let me mark with this color. Yeah, BCA. First option is correct. So I hope you have understood and got a clarity regarding this SN1 and SN2, which is really important topic in this particular chapter or overall organic chemistry, because they will ask so many questions based on this SN1 and SN2 only. So you need to have a clear idea about these mechanisms, this nucleophilic substitution reactions. So yeah, whatever I have told you, the important points over here, you just note it down. I have told you the, like, how these SN1 SN2 differs, and I have explained you the differences also. And yeah, one more thing, this aryl and vinyl halides won't undergo SN1 SN2 in normal conditions. And yeah, these and all I have explained you. You just note it down if you want, or else you just see the video. All right, if you think this video was a little bit slow, you can watch it in a 2x speed. And yeah, that's it for this particular video. We have solved few questions which involved in this SN1 and SN2 mechanisms, or this topic. So which involved in this nucleophilic substitution reactions. All right, and we will solve. I'll try to cover all the previous year questions in this videos. So I hope these videos will be helping you people. And yeah, that's it for this particular video, and we'll meet in my next session. Till then, just be happy and take care of yourself and be kind. Bye.